Our next speaker, invited one, is Alexander Mook from Technical University of Munich in Germany. So Alexander obtained his PhD in physics at the Max Planck Institute of Microstructure Physics in Germany. Then he became a postdoc with Professor Ingrid Mertig at the Martin Luther University of Halle-Wittenberg. And in 2019, Alexander received the George Endrich postdoctoral fellowship of the Center for Quantum Science and Quantum Computing. Now, he is a junior group leader in the group of Professor Johannes Snow at the Technical University of Munich. Today, he will speak about interacting topological magnons. So, Alexander, thank you for being in this conference, and I give you the talk.
Thank you very much, Maria. Thank you very much for putting together such a great conference and for inviting me. It's a great pleasure to participate. So here in this talk, I would like to introduce you to the field of topological magnons. And in particular, I will talk about how the interactions between magnons, so many body interactions, can bring about topological features in the spectrum of these magnons. First, however, let me give you the big picture. This work is motivated in large parts by the challenge to develop technologies with a minimal environmental impact from their power requirements. We have the problem at the moment that with CMOS technology, we produce too much waste heat, and this is why we can't scale CMOS technology any further. One idea, of course, to produce these technologies is to rely on Spintronics. The idea is that we encode information not in the charge signal, but in the magnetic signal or the spin signal. And we can even further reduce the power requirements if we convert this magnetic signal into a signal of magnetic excitations of a magnetic insulator, because these excitations don't carry charge and then there is no Joule heating. The idea would then be to do all the heavy lifting, all of the computations in the magnonic realm, and convert the signal back to the electronic world only as necessary. So these information carriers, these magnons, are shown in a small animation here. Those are the excitations above some ground state. Here, for example, is the ferromagnetic ground state, and the systems we are interested in can be described by such an Hamiltonian. It's a magnetic insulator with localized spin moments at the lattice sites I and J. And these spin moments are mutually interacting with some interaction matrix, and they can also be manipulated by an external magnetic field. Now, in contrast to electrons, magnons, or bosons, so we have to put them into the system, we have to excite them to put them into existence. And magnons carry spin and heat, but no charge, which is why there's no Joule heating. Now, why would you use magnons rather than, for example, photons? The idea is that for magnons, you get ultra small wavelengths, which is why you can really miniaturize the devices. And another reason is that magnons are strongly nonlinear, so they are interacting, which makes actually many of these applications possible. But magnons also have a main problem. Since magnons exist in the collective environment of the solid state, they are interacting, for example, among each other and also with the phonons, for example, and this is why magnons decay. There are two main sources of magnon decay. One is magnon defect scattering, and the other one is many-body interactions with phonons or other magnons. As far as magnon defect scattering is concerned, we can try to circumvent it by relying on our knowledge of topology. Let me here quickly help you to recollect what you know about topological materials. I remind you of the quantum Hall effect, where you have these semi-classical skipping orbits at the edges of the material that constitute chiral edge states. You would also find them in Chern insulators, where in K-space you would have the situation of a fully occupied valence band, an empty conduction band, and then in between a topologically protected metallic state, which is the chiral edge state. Now, if you have an electron in this state, it can't backscatter at defects elastically, simply because there is no other state at the same energy to backscatter into. And this is why transport with edge states is robust. The idea is now that we can realize something like this also with magnons, or more general with spin excitations in magnetic insulators. I will go into the details in a second. For the moment, let me just say that one can realize such a situation in ferromagnets, for example, here on the cargo lattice. If you calculate the magnon spectrum of such a system, you would find that it looks quite reminiscent of the churn insulator. You have these bulk bands of magnons that are separated by a band gap, and in between them, you get these topological chiral edge states. Now, in contrast to electrons, we don't have a Fermi level for magnons, which is why zero energy is at the very band bottom. So we have to put energy into the system to excite a magnon. But once we do so, we would excite such a chiral edge magnon, then it can't backscatter. It defects simply because there's no other magnon at the same energy to backscatter into. So the situation in our mind looks like this. We have such a topological magnon material. We excite it somewhere here, encode information in the magnetic signal, and then it goes around the sample unidirectionally because it's a chiral excitation, and it would go around corners, it would go around defects, and it's not perturbed by any disorder because the state is topological. And now we would bring together the absence of Joule heating with the absence of backscattering, and that could be useful for magnonic application. Now, for the rest of the talk, I will not use this classical language where we would say, okay, we can calculate these magnons by linearizing the Landau-Lifshitz-Gilbert equation that describes the precession and the damping of a magnetic moment in the collective field of its neighbors. From the diagonalization, you would get these spin waves. I would rather look at the quanta of these spin waves, which are the magnons. And for that, I introduce here the Holstein-Primakov transformation from spin operators S to bosons A. So in full glory, it's written here, but it's not too important how it looks like. The main point is that there are these F objects, which themselves are defined in terms of a square root of these bosons, of these magnon operators A. And you have to expand the square root to make sense of the Hamiltonian. And once you do that, you expand the F, put it into the S, and then you take the S and put it into the spin Hamiltonian. You get an expansion of the spin Hamiltonian in terms of bosonic operators, where H0 does not contain any bosons. This is just the classical ground state energy. Then you have H1, which has to vanish if you expand around a stable ground state. Then H2 is a bilinear of bosons. So this describes the non-interacting physics, which can be diagonalized to get the magnon spectrum. And anything beyond H3 and H4 describes many-body interactions between magnons. Now, let me explain to you why we would get these topological magnons. And for that, let's have a look at a ferromagnet on the honeycomb lattice. Let's assume that only nearest neighbors are interacting with a ferromagnetic exchange to stabilize the ferromagnetic order. Then we can perform this Holstein-Primakov transformation. We would get some classical ground state energy, H2, and terms beyond. Let's focus now on the bilinear theory. We can diagonalize it, and then we would get a spectrum that we know already from electrons in graphene. In particular, we get a spectrum with Dirac cones at the K and K prime points of the hexagonal Brillouin zone. Now, these Dirac cones are stabilized by an effective time reversal symmetry, and by that I mean the following. You can apply actual time reversal, which would flip the direction of the spins, but then you can rotate back in spin space simply because the Hamiltonian is isotropic in spin space. And since you can rotate back, you can map a time reverse texture back onto the original texture, and this stabilizes these Dirac cones. Now, to lift the Dirac cones, we have to break spin space isotropy. We do so by introducing second nearest neighbor Dzialushinsky-Moria interaction, which is defined by a vector that multiplies a cross product of two spins. And these little vectors are indicated here by these arrows that connect second nearest neighbors. Once you now diagonalize this spectrum, you would find that the Dirac cones are lifted, and then you can calculate a topological invariant of the lower band because you now have a band gap. The topological invariant that we calculate is the Chern number. It's defined as an integral over the Berry curvature, which itself is given in terms of the eigenfunctions of the magnons. This is not too important here. The main message is this topological integer is non-zero. And then by virtue of the so-called bulk boundary correspondence, this tells you that there has to be an edge state at the edges of the sample. That is the moment you introduce, you terminate your sample, you get an edge state. So what's crucial here is that you have to break the effective time reversal symmetry of the ground state and the spin Hamiltonian. Once you do that, you can perform classical simulations. For example, you can stack such honeycomb ferromagnets in a particular way. And then you can realize the situation where you get a chiral edge state that goes around the hinges of a three-dimensional chunk of your material. Here I show one simulation without disorder and one simulation with disorder. In both cases, you can see that there is this chiral edge state. And even in the case with disorder, although there is some blurring effect, you can still see that the chiral signal is going around the sample, which tells you that these chiral edge states are really robust. Now you can realize many more topological magnon phases. Beyond these churn insulating phases, you can also realize so-called helical edge magnons, where magnons of different spin directions and antiferromagnets propagate in opposite direction at the edges. And you can also realize three-dimensional topology. You can realize vial magnons, so-called nodal line magnons. I will not go here into the detail. I will, for the rest of the talk, focus on these chiral edge magnons. Now the question is, what does it take to get topological magnons? I explained to you so far that we can get them in the case of a ferromagnet with this Dzierzynski-Maria interaction. And this can be realized not only on the honeycomb lattice, but also on the cargo-meat lattice, for example. Another possibility is to use squeezing effects. And by squeezing, I mean that we do not look at magnons that precess circularly, but elliptically. If you have an elliptical axis indicated here by this little in-plane rod without an arrow, and if this anisotropy axis rotates as you go around one of the plaquettes, one of the triangles of the cargo-meat lattice, for example, the elliptical axis of the precession rotates as you go around, and this also introduces a Berry phase and topological magnons. Something like this can also be realized, for example, on the honeycomb lattice in the field polarized phase if you have Kitaev interactions, for example. And then another idea is to realize non-collinear textures. If you have a texture that has a finite scalar spin chirality, so finite opening angle, then you would also realize topological magnon phases. Something like this is found, for example, in skyrmion crystals. The main message here is, if you want to realize topological magnons, then you have to rely on non-Bravais lattices, either non-Bravais in the sense that the structure is non-Bravais, or non-Bravais in the sense that the magnetic sublattice, or the magnetic superlattice, sorry, brings this non-Bravais structure. Now, to conclude with the introduction, there are like two experimental techniques that we can use to study topological magnons. One is so-called neutron scattering. Neutron goes in, it scatters with the magnon, neutron goes out. And then by looking at the inelastic signals, you see that, for example, in this material here, you see two magnon peaks separated by a band gap, and the microscopic modeling would tell you that the system is topological. Then you can also perform transport similar to the anomalous Hall effect of electrons, where you get a transverse charge conductivity. From magnons, you get a transverse thermal Hall conductivity. This means you apply a temperature gradient in y direction, and you get a result, as a result, a heat current in x direction. And this thermal Hall conductivity has been measured, for example, for lutetium vanadide, where you see as you cool down the sample and you get magnetic order, you get a finite thermal Hall conductivity. Now, many materials have been discussed in the context of magnon topology. Here, I just emphasize that these very prominent, famous monolayer ferromagnets, van der Waals materials, chromium triiodide, for example, is also discussed in this context. Now, what's now the crucial question from a theoretical point of view, which is what I'm going to focus on for the rest of the talk. If we want to use these topological magnons for spintronics or also for quantum computation, where we have shown that you can use these topological magnons to entangle two spin qubits over long distances, then you have to ask the question, what is actually happening once you have many-body interactions between these magnons? The fundamental difference to electrons is that magnons do not come with a particle number conservation law, which makes many-body interactions possible that you would not find for electrons, in particular these number non-conserving interactions, H3, where one magnon is destroyed, for example, and two others are created. And this is what I would like to focus on for the rest of this talk. I will quickly show you two examples. One is, I will show you an example how these many-body interactions can actually coarse topological magnons. And the other example is that these particle number non-conserving many-body interactions actually can produce exotic hybrids between magnons and so-called bimagnons that I will introduce later. Now, this work has been done in collaboration with the groups at the University of Basel. It's a collaboration between the groups of Daniel Loss and Jelena Klinovaya and the PhD students, master students, and postdocs in this group. But I also show results from a Japanese-German collaboration with Matthias, Alberto, and Paul. Now, the first thing that comes to mind if you speak about many-body interactions and particle number non-conservation with magnons is that magnons get damped. And this is like the pessimistic view on things. Because H3 is, in mathematical terms, written like this. One boson is destroyed, two others are created. So that would bring in the many-body language a Feynman diagram like the one shown here about one magnon comes in, disintegrates into two others. Then to calculate the self-energy, we have to recombine the two to get, again, the single particle propagator. And the main message here is that, in principle, if a magnon can disintegrate into two others, then the original magnon, of course, has a finite lifetime, and that would cause some blurring in the spectrum that you would measure, for example, with neutron scattering. In particular, something like this has been seen for magnetic excitations in a quantum magnet, where you get a clear single particle excitation, which then suddenly terminates simply because the kinematic possibilities of this excitation to decay are suddenly so strong that the quasi-particle peak is completely wiped out. And now this is a problem for topology, because in the non-interacting language, we say, okay, there's this interesting topology, and we talk about gaps between magnons and in-gap chiral states. But if the quasi-particles just disintegrate and get wiped out, then it also jeopardizes the notion of topology. There are ideas to use non-Hermitian topology to take into account the lifetime broadening, but here I would actually like to focus on an optimistic question. Rather than asking if the damping destroys the interesting physics, I would like to tell you about the situation where this kind of interaction actually brings about topology. And for that, I will look at a situation like this. Now let's assume that you have a spin Hamiltonian and a particular magnetic ground state that breaks some symmetry S. And for the sake of concreteness, let's assume that it is this effective time reversal symmetry that I was talking about in the beginning. Now the situation can arise that as you do this magnon expansion, that the free magnon part actually respects the symmetry. It does not account for the breaking of the symmetry. And then the lowest order term that can account for the breaking is this cubic term, which is the particle number non-conservation. So let's have a look at a situation like this, where H2 has this artificial symmetry S, which the total system doesn't have, and only interactions would account for this situation. For this, let me introduce two other honeycomb lattice ferromagnets. Once we look at an in-plane magnetized system, and for the other system, again, at an out-of-plane magnetized system. And in both cases, we assume that there's ferromagnetic exchange interaction. And for the first model, we take again the second nearest neighbor Zerleshinsky-Moria interaction that points out of plane. And for the other model, we assume that we mount this two-dimensional spin system on a substrate such that we break inversion symmetry and then get interfacial DMI indicated here by nearest neighbor in-plane DMI vectors. The Hamiltonians just look like this. They look rather similar. And as you now do the magnon expansion, you would find that in both cases, you would get a free theory that only sees the Heisenberg exchange and the magnetic field, but not the DMI. The DMI only appears in the cubic terms. And this is because the systems are chosen such that the magnetic direction, the magnetization direction, and the DMI are orthogonal to each other. And this is then the reason why you wouldn't see the DMI in the bilinear terms. Now let's discuss symmetry. For the model that I call the A-chiral model, you can flip time, which flips the magnetic moments, but then all of the DMI arrows point in the same direction. So we can take this direction in spin space and rotate back this spins about this direction. So we can map the texture back into the original texture, which tells us that here time reversal symmetry is not broken. In contrast, in this case, when we flip the magnetic texture, we cannot rotate back in spin space because the DMI vectors actually span a plane. And then this means that the DMI term of the Hamiltonian is not invariant under this 180-degree rotation. So here we would expect that the cubic terms account for symmetry breaking. Now let's have a look at the actual calculation. So if you just diagonalize the free part of the Hamiltonian, you get these white bands, which are the free Magnon bands, again with the Dirac cones at the K and K prime points. And what you see in the background is the so-called 2 Magnon density of states that I will talk about in a second. For the rest of this talk, I will focus now on this little red region here, just in the vicinity of the Dirac cone. So let's have a look at the blow up. This is now a blow up, and this is the energy region about the Dirac cone, where I call 0 energy, where we have the Dirac cone in the free theory. Now what we do is lowest order many-body perturbation theory. So we calculate the interacting Magnon-Green's function from the lowest order self-energy due to these bubble diagrams I've been talking about. And we extract from it now the spectral function, which is plotted here. And you can see in this tomographic-like plot that exactly at the Dirac cone, you see, okay, there's some renormalization, but the Dirac cone in the achiral case is actually stable. So interactions do not lift the Dirac cone in this case, which goes hand in hand with our argument that time reversal symmetry is not broken. However, in this case with the chiral magnet, we see that in the renormalized spectrum, we get a gapped Magnon spectrum because the interactions lift the Dirac cones and break time reversal symmetry. Now we show in our publication in detail that we can prove that this lifted Dirac cone amounts to a topological gap. In particular, we can show that with open boundary conditions and including these many-body terms, we would find the situation that at the right side of the sample, we see in the spectral function that there is a state with positive group velocity. And at the right side of the sample, there's an edge state with negative group velocity, which means overall that there is a chiral state that goes around the sample. And this indeed tells us that the system is topological. So we have a topological system caused by the interactions between magnons. We can now have a look at this gap and how it changes as we decrease magnetic field. So at large magnetic fields, we have a small gap, which increases a little bit and we get a downward renormalization, but then suddenly the situation changes and we get this blurred spectrum. And this is because for lower magnetic fields, we have the continuum of 2 magnons, which is a combination of any free 2 magnons. And since then the single particle peak enters the continuum, the single particles can decay again, and this dilutes the single particle peak. Now the question is this an artifact of many-body perturbation theory? And for this, we have to compare it now with a non-perturbative method, where we rely on density matrix renormalization group and a time evolution based on matrix product operators. I will not go into the details, but just tell you the following. We will now look again at large magnetic fields. Now we call the magnetic field HC. And what I plot here is the dynamical structure factor, which is just like the spectral function essentially, particularly at the K point. So for large magnetic fields, we expect from our many-body perturbation theory a small gap. And this is what we see here. We have the single particle peak, but we can't resolve the gap simply because numerically that's not possible in this particular realization. However, we see as we decrease the magnetic field, so we go a little bit closer to this large splitting, we see that this peak splits into 2, and indeed we see the splitting of the 2 Magnon bands. And now in perturbation theory, we expect the magnons essentially to become diluted at low magnetic fields. However, in this non-perturbative quantum calculation, we see that these 2 split Dirac cone peaks do not enter the continuum, which is this region here. Instead, they get repelled by the continuum, such that we can extract the information that Magnon topology that is caused by interaction is actually stable against decays, simply because the interactions pushes the topological single particles out of the continuum. Now, in the final 2 minutes, I will just show you an example of topological hybrids between magnons and other excitations that I call bimagnons. And the introduction to this is very simple. So a magnon is simply a superposition of a single spin flip in a ferromagnetic lattice. So we would take states like this, where we have a flipped spin, and we would construct a Bloch wave out of states with a single spin flip. And we would introduce the momentum to characterize this magnon state. Now, if we have 2 spin flips, then we would have to pay energy penalty for each of the spin flips. One spin flip has a penalty of 4 because there are 4 frustrated neighbors. And if the 2 spin flips are far apart, we have to pay a penalty of 8 neighbors. However, if we bring 2 spin flips close together, the effective surface area of this block is only 6 spins, which is why there is a potential energy gain associated with 2 magnons binding together. This is why you can get 2 magnon-bound states below the continuum of magnons. In particular, you can get the situation where the magnon energy crosses the energy of these bound states, or I will call them bimagnons here. And now we would look at the situation where these 2 states hybridize and produce an anti-crossing, and in particular an anti-crossing that is topologically non-trivial. So we now look at the basis of the sub-Hilbert space of single magnon excitation and 2 magnon excitations, where the 2 magnon states are characterized by the center of mass momentum and the relative distance between the 2 spin flips. Again, we will rely on interfacial DMI, because if you rewrite this interfacial DMI, you will find that it couples a Z component of spin with a ladder operator of spins, which in the magnonic language amounts to this particle number non-conserving term, which generates a finite matrix element between these 2 magnon states and single magnon states. And now let's have a look at a particular realization on the square lattice of a spin 1/2 system, where we assume that there is ferromagnetic nearest neighbor interaction, I1, a third nearest neighbor interaction, and a DMI term. If we only have nearest neighbor interaction, which is isotropic, so the Z components of the spins are similarly interacting as the X and Y components, we get the 1 magnon state, the usual cosine band with this parabolic behavior around the gamma point that we are used to from ferromagnets. And in gray, you see the 2 magnon continuum, which is just a combination of any 2 single magnon states. But below the continuum in red, you see that there are these bimagnons that bind together because of this potential energy gain of putting 2 spin flips together. If we look at an anisotropic situation, where now we have Ising anisotropy, we would gap out the magnon spectrum. The continuum is also shifted towards higher energies, and the bimagnons actually completely separate from the continuum. And by playing around with third nearest neighbor interaction, we can realize the situation where the bimagnon energies cross the single magnon energies. And then by introducing DMI as advertised, we would get these avoided crossings, and we can calculate Chern numbers, which turn out to be topologically non-trivial. And indeed, if we look at the edge spectrum, we find that there are these chiral edge states that connect 2 topologically non-trivial bulk bands. Now, why is that possible? I told you in the beginning that magnon topology relies on non-Bravais lattices. Here, however, due to the combined topology between magnons and bimagnons, it is as if we are effectively on a non-Bravais lattice, although the structural lattice is a Bravais lattice, a square lattice. And this is because although the usual magnons live on the original square lattice, indicated here by these yellow blobs, a bimagnon describes 2 spin flips either connected along X or Y direction. So the center of mass of bimagnons lives at the bond midpoint, such that effectively we are now looking at a hopping model on the leap lattice, which is a non-Bravais lattice, and this generates then the possibility of magnon topology. One can play the same game also for spin 1 magnets, which bring about another type of bimagnon, a so-called single ion bimagnon, where you can put 2 spin flips on the same side. The story is very much similar. You can get a hybridization effect and eventually chiral edge magnons. So my last comment is that you can differentiate topological magnons from topological magnon-bimagnon hybrids by an analysis, in particular in the classical limit, because topological magnons also survive taking the classical limit. So you find topological magnons in particular just from solving the Landau-Lifshitz-Gilbert equation. However, these topological magnon-bimagnons from these non-conserving many-body interactions rely on the system being quantum. So you really need a finite spin quantum number. Otherwise, those effects would disappear. Such effects have already been seen in neutron scattering, for example, in the spectrum of triplons in two triplon bound states, but also in the spectrum of magnons in iron diiodide, where you have one magnon and single ion bound states that show a clear hybridization and anti-crossing. With that, I would like to close. The main take-home message here is that magnon-magnon interactions can cause novel topological effects in quantum magnets. I have shown to you two examples, and I would like to close with advertising that I will be moving soon to the University of Mainz, where I will build my own research group, where the funding comes from the German Research Society within the Eminöter program. And if you are a PhD student and postdoc and are interested in these topics or similar topics, or if you know someone who is, please feel free to contact me. I would be very happy to talk about the possibility of PhD positions or postdoc positions. And with that, I would like to thank you very much for your attention.
Thank you, Alexander, for this very nice talk. I see that Jan has raised his hand. Please, Jan, go ahead.
I'm clapping.
Ah, okay.
I'm not raising my hand, I'm clapping.
Good, this is also good.
I already talked with Alex about everything, so no questions from my side at this moment.
Good. I don't know if there is anyone in the audience that has any question. I cannot see any in the chat. No one. Then I may ask you something. So about this bimagnons, I saw you saw at the very last slides of your presentation that there are some people that has already seen them, right?
Right, exactly.
Can you go, because I'm not an expert on this field, but can you maybe go a little bit deeper on these images?
Yes, so what you see here is neutron scattering data, so energy over momentum transfer. And typically, if you measure magnons, you would get rather clear single particle peaks. And here you really have to look into the detail. One would find that you cannot explain this spectrum simply with single magnon excitations. You would need to take into account these single ion bound states, or what I call the bimagnon, to account in particular for this avoided crossing. So this dark region between these two yellow regions. And one can show that this has to be a result of a hybridization between single magnon excitations and this rather new, unexpected peak in the system, which is then attributed to the bound state. A similar situation holds here for triplons. This is not a magnon, but here you have a singlet ground state, and you look at the triplet excitations, which form a quasi-particle that is called triplon. And there again, you see that there are these parabolic bands at the top that cross these more dominant, more bright features here. And this is because typically you wouldn't expect to see two-body excitations, two triplons, or also single ion bound states. And it's only the hybridization with the single particle excitations which makes them visible. This is why the two triplon excitations are very faint up here and become more visible as you lower their energy and make them hybridize with the single particle excitations.
Okay, thank you for this nice explanation. Rodrigo is asking you if these topological magnons are confined to the edge states in the real or K space?
The edge magnons are confined to the edge state, to the edge of the sample in real space. So whenever I show a figure like this, then this means that there is still one momentum direction along the edge, which is, this momentum is still a good quantum number, but you have open boundary conditions in the opposite direction. And then these orange features that connect these continua that are gray are then the edge states really at the edge and the opposite direction. So one edge state lives at at the right edge, for example, and the other one that with the opposite chirality on the other side of the sample.
Okay, thank you. Oh, we have another question in the chat from Matt. Could this bimagnon state be proved via BLS, or does this symmetry not favor this?
So typically you would not expect, I guess, to measure them because you would have this dipole selection rule, which would tell you that you only can measure dipolar excitations, which would be magnons. But if these bimagnons interact with the dipolar interactions because of number non-conservation or spin non-conservation in the spin language, then there is a chance that you would see bimagnons. But of course, with BLS, you would have the problem that you have to find these bimagnons at gigahertz frequencies, right? And typically in these examples that I have been showing, we are talking terahertz here.
Okay, I'm gonna finish this. I think all of you can join Alexander and all of you now in Gathertown to continue this interesting discussion. I would